Hola, my geometry friends. Welcome to Unit 7, Lesson 11. The time has come to do your most favorite thing of all geometry stuff to do, and that is proofs. So we're doing circle proofs today. And these aren't going to be so bad because unlike the beginning of the year when we very first started doing proofs, now you are more familiar with them. But there are a lot of rules that are new to this unit with the circle stuff. So let's start by going over those, shall we? Okay, things to look for while we're doing circle proofs. In the diagram at the right, why could we say that angle CAD is congruent to angle CBD? Or why could we say that angle ACB is congruent to angle ADB? Well, the reason why, inscribed angles that intercept the same arc are congruent. So hopefully what you're recognizing here with these angles, ACB and ADB, ACB and ADB, both intercept the same arc, so they are half of the same measure, so they are equal to each other. So both of those angles intercept the same arc, so they are both half of measure of angle A, or measure of arc AB. Same thing happens on the other side. Angle ACD over here, and then angle CBD over here, both intercept the same arc of CD. So then both of those angles are half the measure of arc CD, so they are equal to each other. As we are doing proofs, what we will say is inscribed angles that intercept the same arc are congruent. There are two rules that are very similar to each other. So we have to make sure we have the wording correct. These are two different inscribed angles that intercept the same arc. So inscribed angles that intercept the same arc are congruent. Next, we watched a video on this. In the diagram below, if JK is a diameter, then what would we say about angle JLK? Well, angle JLK would be half of the intercepted arc. Since JK is a diameter, then JLK is a right angle. Now, in our proof, we can say just Thales' theorem. It is okay to just write Thales' theorem and then move on to the next step. You can just write that as the reason why angle JLK is a right angle. Or if you don't remember that, you can say an inscribed angle that intercepts the diameter is a right angle. You could also make the longer description about how JLK is half of arc JK. Since arc JK is 180, JLK is 90. But the shortest way is to just write Thales' theorem. Don't forget your apostrophe because his name ends in an S and it's possessive. Okay, so then our next rule. What statement can be made if it is known that arc ST is congruent to arc RV? And then what is the reason? Well, what we can say is that angle SRT is congruent to angle RSV. This is very similar to our first fact that we wrote down, this one. Inscribed angles that intercept the same arc. These inscribed angles go to the same arc, arc AB or arc CD. Now, the two different inscribed angles intercept different arcs, but the two arcs happen to be the same measure. So we have to say inscribed angles that intercept congruent arcs are congruent. There is a slight difference, but a slight difference in the picture, a huge difference in the meaning. These two inscribed angles intercept two separate arcs. So you can't say the same thing as what we did in the first one. So angle SRT intercepts arc ST. And then angle RSV over here intercepts arc RS. But since the arcs are equal, then the inscribed angles are equal. Now, if we draw in RV, this is to draw in RV and ST, those chords are congruent because congruent chords that intercept, there it is, congruent chords that intercept congruent arcs, congruent chords, sorry, I was messing around trying to find where I hid the information. There we go. Okay. Congruent arcs intercept congruent chords, and we can write that both ways. We happen to know that the arcs were congruent first. So because the arcs are congruent, then the chords are congruent. If we had the information the other way around, if we knew the chords first, then we could say that congruent chords intercept congruent arcs. This time it's congruent arcs intercept congruent chords. So it goes both ways. So make sure you have both pieces of information down. Similar diagram. Now we're talking about arc RST and arc RVT. RST is the top part of the circle. RVT is the bottom part of the circle. We do not know whether RT is a diameter or just a chord. So we have to go on the assumption that it is not a diameter, just a regular chord. But what's going to be true about those two big arcs? Well, those two arcs make the full 360. So we know that the sum of the measures around a full circle is 360. That means all the parts, all the different arcs that add up to make the full circle, all those arcs add up to equal 360 degrees. Okay, sum of the measures of the arcs of a circle is 360 degrees. When doing proofs that contain a circle, we have to look for some certain things that we have done before. An angle formed by a tangent and a chord is half the measure of the intercepted arc. An angle formed by a tangent and any chord. We know that the tangent line is perpendicular to the radius or diameter, but if our tangent line touches a chord that's not a diameter, then the angle is half the intercepted arc. So sketch in a tangent line and draw a chord that goes from that point of tangency. The tangent line is the tangent line creates an angle that's half of the intercepted arc. Remember, the intercepted arc is the arc that is part of the circumference of the circle that goes from the point of tangency to the other end of the chord. So that is our intercepted arc. So the angle measure formed by the chord and the tangent line is half of that measure. Congruent central angles intercept congruent arcs, and congruent central angles intercept congruent chords. This information can be written in any direction. And what I mean by that is if you're given the equal central angles, then you can conclude that you have congruent chords and you have congruent arcs. If you are given the congruent chords, then you can conclude you have congruent arcs and congruent central angles. If you are given the congruent arcs, you can conclude you have the congruent chords and the congruent central angles. So one pair of equal pieces will lead to the other two pairs of equal parts as well. Okay, so equal chords, congruent chords intercept congruent central angles and congruent arcs. And they all come in a package deal. Radii and tangent lines are perpendicular at their point of intersection. This one we've done several times, both when we were writing the equations of lines and again when we were doing our constructions. So if you draw in your radius BC, or maybe you extend it to make it a diameter, either way, that diameter or that radius is perpendicular to our tangent line at the point of tangency. It makes a right angle on each side. An old rule Next would be an old rule we have been doing all unit long. An inscribed angle is half the measure of the intercepted arc. We were just talking about how central angles are equal when the intercepted arcs are equal. That's because the inscribed angles are, the central angles are equal to the intercepted arcs. Inscribed angles are half the measure of the intercepted arcs. Now, along with all this circle stuff, we still have rules with triangles that are congruent, CPCTC, triangles that are similar, CSSTP, all radii of a circle are congruent. If a chord and a diameter are perpendicular, then the chord is bisected. If the chord is bisected, then it has to be done at a 90-degree angle, as long as it's a diameter or a radius. Proving triangles similar, remember, is angle-angle similarity. Corresponding sides of similar triangles are proportional. That's your CSSTP. One of the rules we did in lesson 10, two tangents from the same external point are congruent. We can still use reflexive sides, reflexive angles, so reflexive property is still in play. And we might have to draw in auxiliary lines sometimes. All that stuff that we have done in the past is still live and in play. Okay, so shake it out. Let's do a proof. What we're going to do is prove that the opposite angles of a cyclic quadrilateral are supplementary. So we're going to prove one of the theorems that I gave you early on in this unit. That means we are trying to prove that the measure of angle ABC plus the measure of angle ADC add up to 180. The opposite angles in our quadrilateral add up to 180. We're trying to prove that. So the first thing we have to do is write in whatever's given. And the only givens that we are starting with that we have right now is that we have a cyclic quadrilateral called ABCD. The cyclic quadrilateral means it is a four-sided shape with each vertex on the circle and the sides are chords. So it's an inscribed quadrilateral. We are supposed to figure out how to make the opposite angles add up to 180 degrees. Now, angle CEA is an inscribed angle. And angle CDA is also an inscribed angle. So that means those inscribed angles are half the measure of the intercepted arc. So the measure of angle D is half of the arc ABC. And the measure of angle B is half of arc CDA. By one of the rules we just wrote down on the previous page, an inscribed angle is equal to 1/2 the intercepted arc. Inscribed angles are half the intercepted arc. One of the other rules we wrote down earlier is that all the arcs around a circle add up to 360 degrees total. So that means that arc ABC on one side and arc CDA on the other side, that completes the circle. So those two arcs add up to 360 degrees. So the rule that I told you to write down for when we use this is the sum of arcs of a circle equals 360 degrees. So we're getting there. I have an arc ABC and arc CDA adding up to 360. So now what we can do is just take half of everything in that equation. So I'm going to take the equation from step 3 and basically just divide everything by 2. That is the division property of equality. Technically, since I wrote it as 1/2 times everything, I guess I should have put multiplication property of equality. So if you multiply by 1/2, that's the same thing as dividing by 2. So it really doesn't matter how you write it. It works out the same every way. But now I have 1/2 the measure of arc ABC plus 1/2 the measure of arc CDA equals 180. Now I can do a substitution from step 2 to get my angle measures to add up to equal 180, which means they are supplementary, which proves that opposite angles of a cyclic quadrilateral are supplementary. By definition, supplementary means they add up to equal 180s. If you need more time to write, hit pause. Otherwise, I'm moving on. Proof number 2. Given the circle O, notice that the center point is not given, so we don't have to be confused about whether we have diameters or not. We do not have any diameters. We have chords SA and TK intersecting at point N. We're trying to prove that TN times NK equals SN times NA. We are proving the rule that you were using a few days ago, that the product of the parts of two intersecting chords are equal to each other. So if I do A times B, that would equal C times D. This is the way we wrote the rule earlier in the unit. Tn and Nk, Sn and Na would be the same segments, either A, B, C, or D. See how Tn would be an A, Nk would be B. So we're going to try to prove this theorem that the product of the parts of intersecting chords are equal. So we start with our givens, all that wonderful given stuff. If I'm going too fast, just pause it, fill in, and then come back. All right, step 2. Well, I guess what we should do first, before we go too far, is fill in our auxiliary lines. We do need a couple auxiliary lines here. So my auxiliary lines, I guess I'll do an orange because I like orange. We're going to draw an auxiliary line TA. I don't need two of them. I need one good one. Auxiliary line TA and auxiliary line SK. Those auxiliary lines help me create two triangles. So in order to get to this multiplication of segments, we need to remember how to prove two triangles similar. So we are going to prove these two triangles that we just created similar. And to prove triangles similar, we need angle-angle similarity. So we need two pairs of congruent angles. So here we go. Angle SNK and TNA are vertical angles. That's probably the easiest and most obvious pair of angles that we are going to get congruent. Next, we need another pair of equal angles. So we have some options here. I'm going to use angle ASK and angle KTA. If you look at angle ASK down here and KTA up here, what you notice when you trace their sides, they both have intersection points on the circle at A and at point K. That is two inscribed angles that intercept the same arc. If two inscribed angles intercept the same arc, then they are congruent. So there's our second pair of equal angles. Once we have two pairs of equal angles, we have our triangles similar by angle-angle similarity. And hopefully you remember that you can take the cross product that was given, the multiplication of the segments, unwork it and go backwards and set up the proportion. That was your corresponding sides of similar triangles are proportional, CSSTP. And then we use the cross product property and we write out cross product property to finish off our proof. All right, moving on. Proof number 3. This time we're going to prove that the tangent squared is equal to the part of the secant times the whole secant length. So we're going to do a proof of the calculations you were doing from lesson 10 that proves that tangent squared equals part times whole. Before we go too far, we again are going to need to put in some auxiliary lines that would help us generate some triangles. So we're going to connect T to G with an auxiliary line, and then connect A to G with an auxiliary line. Now, may not be as obvious here to see what triangles we're using, so let me do this. Using that big one, NTG, and then the smaller one, TAG, TAG. So we are going to prove these two triangles are similar, and then use what we did in the last proof, CSSTP, make a proportion, and then cross product property to multiply. So somehow I need to get NG times itself. Okay, so with all proofs, we start with our givens. Circle O, we have tangent NG and secant NT, that was given. So here's what we're going to do. If you look at, oh, wait a minute. This is not the right triangle. As I was talking and coloring this in, I get so excited to color. I realized that using the original triangle that I just colored in blue, we wouldn't have NG used twice, once for each of the different triangles. So we need this triangle over here. My apologies if you colored in your paper and you have to erase it. Even more apologies if you colored in your paper and you can't erase it. Okay, so eventually what we'll need is NG, which is a side of each of the two different triangles to be multiplied times itself. So when we get to it at some point, we will take this cross product and unmultiply it to make our proportion, and we would need NG from one triangle to eventually be multiplied times NG from the other triangle. And then the other two sides, AN and TN, can fill in whichever two spaces we want. But the NGs need to be diagonal, one from each of the different triangles. All right, now with those adjusted, we can use angle N, because we are using similarity proofs in order to set up the proportion. Angle N is reflexive with both triangles. So we're going to do that first. Now, using the rules that we know about intercepted arcs and angle measures, we can say angle NGA, angle NGA, which is an angle formed by a tangent and a chord. An angle formed by a tangent and a chord is half the intercepted arc. That was one of the rules we went over at the beginning of this video. An angle formed by a tangent and a chord is half the intercepted arc. Another one of the rules that we went over at the beginning of this video was that an inscribed angle is half the intercepted arc. So our inscribed angle of ATG is half the measure of arc AG, because an inscribed angle is half the measure of the intercepted arc. If you notice, both of those previous steps use 1/2 arc AG. So if NGA and NTG are both equal to the same thing, that means they are equal to each other, and you can say either substitution or you could say transitive property. That is now our second pair of equal angles, because the first pair of equal angles was angle N reflexive, angle N congruent to angle N. Now that I have two pairs of congruent angles, I can say the triangles are similar. We can set up the proportion by CSSTP, and then we can use the cross product property, and whammo bam, there's our proof. So we just proved that the tangent squared is equal to the outer piece of the secant times the whole secant length. Pause if you need. I'm going to keep going. Proof number 4. We are going to prove that the outside piece times the whole secant is equal to the outside piece times the whole secant. So it's going to be very similar to the proof we just finished, only this time we're going to prove instead of tangent squared equals outside part times the whole secant, we're going to prove that the outside piece times the whole secant is equal to the outside piece times the whole secant. We do need to put in our auxiliary lines to create the two triangles, so we will connect N to S as before, and then E to A as we did before. And similarly as the last one, the triangles we use will be triangle ESN, the big one there, and then ECA, smaller one up here. So we're going to prove those two triangles are similar, set up the proportion, and then use a cross product property to prove the rule that we've been doing with our calculations. Just like last time, givens at the beginning, we got a reflexive property with angle C. Now, we got to figure out how we're going to get another pair of equal angles. The reflexive property is no big deal. That was pretty simple and straightforward. So what comes next? Well, I'm going to use the fact that we have, let me get a good, yeah. We have here a four-sided shape with all four angles, vertices on the circle. So ESNA is a cyclic quadrilateral. So since that is a cyclic quadrilateral, I know that the opposite angles are supplementary. Makes sense? Opposite angles in a cyclic quadrilateral are supplementary. You may not know exactly why I'm using those right now, but I'm going to tell you we're going to use it to get the measure of angle EAC. Eventually, we will be able to get to the measure of angle EAC equal to angle ESN. We will be able to get those two angles equal. Right now, we have angle ESN supplementary to EAN. Now, if you notice, why would I want those two angles to be supplementary? Well, because with this segment here drawn in, angle EAN is also supplementary to EAC because they form a linear pair. So I have the opposite angles of the quadrilateral adding up to 180 being supplementary, and the linear pair being supplementary. Then we had this thing where we could take the two equations, set them equal to each other, do a substitution, subtraction property of equality, and then get the angles equal. The faster way was to remember our congruent supplements theorem. That means congruent supplements theorem says that if two different angles are supplementary to the same angle, then they have to be equal to each other. All right, so we have two different angles that are supplementary to the same angle. That means that pair adds up to 180 and that pair adds up to 180. Subtracting 180 from each of the sums gives you two equal remaining parts. So that's the congruent supplements theorem. We actually did a proof of that earlier in the year. But that, my friends, is our second pair of equal congruent angles. Now we have our triangle similar. We have our proportion set up for CSSTP, and we have our cost product, BAM, proving that the outer piece times the whole segment is equal to the outer piece times the whole segment. So go back, rewind, watch as much as you want. I know this is great entertainment and super fun. Pause if you're still trying to write this down. And then when you turn the page, you only have 4 problems to do that are all algebra-based problems. One from each of the proofs that we did in class or in this lesson together. So I want you to solve for X in each of the different problems. And then you're going to tell me which proof was used as the reason why you could create your equation. Okay, so that's it. 4 proofs and some review information all done in less than 30 minutes. So I will see you soon. Best of luck and take care.